This short lecture is titled Know Your Forces, How to Identify and Work with Physics Forces. Technically speaking, if you want to get right down to the core fundamentals of our universe, there are exactly 4 forces operating in the universe. The first one is gravitational force. This is the force that holds the stars together in a galaxy, and in this photograph, galaxies together in a cluster of galaxies. Gravity is trying to hold our universe together, and it's failing, actually. The second force that's acting in the universe is the electromagnetic force. Electromagnetic force is the force between magnets. It's also the force mediated by photons, by light. The third force at work in our universe is the strong nuclear force. This image is of the nucleus of an atom, which contains protons and neutrons. You might remember from school that protons are positively charged particles, but positively charged particles repel each other through the electromagnetic force. And so how do you get them all clumped together in this incredibly dense nucleus? Well, there has to be a strong force that overcomes that electromagnetic repulsion and actually winds up binding these together in an incredibly strong object, the nucleus of an atom. The final force that's acting in the universe is the weak nuclear force. This one is actually a little bit hard to explain, but it is what mediates the reaction that makes the sun glow. The weak nuclear force governs the interaction that converts protons into neutrons, and so it governs nuclear reactions, the things that produce power in our power plants and the reason that the sun shines. While it's great to know that there are 4 fundamental forces acting in our universe, these 4 fundamental forces don't really give us practical ways to solve problems. So for applying physics to everyday situations, for actually using it for practical purposes and making it useful, we need a different way of thinking about forces. We need to classify the forces around us mathematically so that we can actually solve problems. And so we're going to break forces into 2 categories. There are contact forces. Contact forces, like the name implies, come into effect when objects are in physical contact with each other, when they're actually touching each other. Another class of force are long-range forces. Long-range forces act between objects even if they're not in physical contact, so if there's a long range or a distance between them. Some examples of contact forces are simple push-pull forces, pushing on something or pulling on it. If you're using a rope or a cable or a string or a chain to pull something, then we distinguish that as something a little bit different. We distinguish that as tension. And the reason to distinguish it is because there could be an engineering problem there. It could be that there's a limit to the amount of force that a chain or a string can transmit. And so we distinguish that as a tension force just so that we're aware that we're using this tool to transmit the force. Drag force is also called air resistance. It's when an object needs to push air or fluid out of the way as it moves. That fluid or air pushes right back on the object due to Newton's third law, and so that's a drag force. Thrust force is an example when an airplane uses a jet engine to propel itself forwards. The force coming out of that jet to move the airplane forwards is called a thrust force. Now these last few, friction, normal force, and spring force, are all a little bit tricky, and so I am going to go through them separately to give you kind of the mathematical specifics of how we determine those. Let's talk about normal force. So normal here, the word normal, it's not as in like opposite of weird. Normal force, normal is another word for perpendicular. Normal force is the force that a surface applies in response to pressure. So as I stand on the floor, my weight is a force. It's definitely pulling me down, but the floor is supporting me. And that support is normal force coming from the floor on my body, and it's directed perpendicularly to the floor. If I were to lean against a wall, press my hand against the wall and push on the wall, then the wall would respond by supporting me, and that normal force, the support from the wall, would point perpendicularly from the wall on my body. So if we imagined a little person sitting on this hill, Here we go. That's some like high-class artwork there. There is actually a normal force supporting this person, and the direction it points is normal to the surface, which means perpendicular to the hill. Just as an example of what normal in normal force means. So let's talk about friction. Friction comes in two varieties. There's static friction for objects that are at rest, and kinetic friction for objects that are sliding, surfaces that are sliding against each other. Let's begin by looking at the static friction case. So we write static friction as a lowercase f, that's how we describe the force, with a subscript of s for static. Imagine that there's a very heavy box sitting on your floor, and you need to push it across the floor. So you begin by pushing very lightly on the box. You're definitely applying a horizontal net force to the box, but it doesn't go anywhere. That's because friction is holding it in place. So you push harder. You double your force. It still doesn't move. Friction is that strong that you doubled your original force and it still doesn't move, and so you push even harder, and finally you find a force that's great enough that you can actually get this thing going. This is kind of the wily thing about static friction. The actual force produced by static friction varies. So we describe static friction as being less than or equal to this kind of maximum level. And the maximum level depends on the normal force. So this is the supporting force of the floor on my box in my example, multiplied by a coefficient of static friction. The coefficient is written as the Greek letter mu. That's a lowercase Greek letter mu. And in this case, this would be a specific coefficient of static friction between, say, cardboard and a wood floor. So the two surfaces involved, the two surfaces which are in contact, have to be characterized for this coefficient of friction. Coefficients of friction are not theoretically determined. They're very difficult to predict. They are empirically or experimentally determined. So somewhere someone has dragged cardboard across wood, and they have measured the friction that happens between the cardboard and the wood. And so if you were engineering a system which involved cardboard and wood, you would look up these values. There's no formula for predicting them. You just look them up. So again, static friction has this maximum value, but it can be less. If you're just pushing lightly on the box in the example, then the static friction just exactly opposes the motion. And so the direction that static friction points, it points whichever way it needs to keep something from moving. And then once you break that static friction, once you apply a force greater than this maximum amount, then you've got a sliding situation and you have kinetic friction. So that's written as a lowercase f with a subscript of k. And kinetic friction is a little bit more straightforward in that it is just straight up equal to the normal force on the object that you're interested in. And so the supporting force from the floor on the box multiplied by, again, a coefficient of friction, but with a k this time, because once objects are in motion, once they're actually sliding, they tend to have slightly different coefficients of friction than when they are at rest and you're trying to get it going. So this kinetic friction, the direction it points, again, is whatever direction it needs to oppose the motion. It always points against the direction that it's actually sliding. So spring force, springs can be leaf springs. Here's an example of one that's used in like automotive suspension. A diving board is an example of a leaf spring, or springs can be these coiled up things that make you think boing. Spring force is described by something called Hooke's law, and it looks like this, that the force on an object is equal to negative k times delta x. So delta x is the amount that the spring is either stretched or compressed, either one, and then this k is something called the spring constant. Similarly to the coefficients of friction, spring constants depend on the material of the actual spring and the way it's constructed. And so spring constants are something that are measured, and that's how springs are characterized. You buy springs with a specific spring constant depending on what force you want for a given amount of compression or extension. So finally, let's not leave out the long-range forces. There are two that come up in introductory physics, and those are gravitational force and electromagnetic force. In the first semester of introductory physics, we usually don't deal with the electromagnetic force yet. We're going to see quite a bit of gravitational force, though, because this shows up to us as weight. So the weight of an object, we usually write this as W equals the mass of the object times the gravitational acceleration, which on Earth is a 9.8 meters per second squared directed toward the center of Earth, which we usually think of as down. But that's a local G, that's local gravitation. For any situation where an object is on another planet or a moon or something like that, you would actually use a different gravitational acceleration. So practically speaking, this is the only long-range force you're going to see, and it's usually going to show up as weight. And that's pretty much it for practical application of forces, for learning what the different forces are and how they're handled mathematically.